Hello, am I audible? Hello, am I audible? Hello, am I audible?
Yes, ma'am.
Yes, ma'am.
Okay, okay, thank you. So I'm sharing my screen. So this is your week 6 of NPTEL live session on the course of Foundations of Cryptography. So as usual, I will first discuss the NPTEL website questions for week 5 first, and then I will discuss the topic for week 6. So let's start with week 5 assignment. Now, first question was, which of the following is or are correct? Block length of 64 bits and a key length of 56 bits are the shortcomings of DES. Is it correct? I think most of the ideas or concepts are already discussed in the last week, and quite a lot of them are even same. So anyone would answer this is correct, this statement? Block length of 64 bits and a key length of 56 bits are shortcomings of DES. Okay, so this is true actually, this statement, because as we know, DES has 56 bit key, and which can be uh, exhaustively search the whole key space. That is, all the 256 keys can be just searched for, and like given a plaintext ciphertext pair, you can try all the possible keys and find out which one matches, so that you get the plain ciphertext for that corresponding plaintext using that particular key. So exhaustive key space search is possible with such small key size, and also for block length 64 bits is another cause of vulnerability of DES, because the smaller the block length is, the higher the chance that in block mode of encryption, so the initialization vector can be repeated, so that probability gets higher with the smaller block length. So we want this block length to be higher. So this statement is correct. Now, AES block cipher is not proven to be secure against computational adversary. Is this statement correct?
Yes, ma'am.
Right. So AES block cipher is basically heuristically secure, but it is not proven to be secure against some computational adversary, which means that there is no such mathematical assumption on which we can rely upon to say that AES is secure. So there are some cryptanalytic approach, and for the long period time, people have tried to exploit the way AES is constructed, but have failed, and so heuristically it is believed to be secure. So this statement is correct actually. A 1-bit change to the input of a DES S box ensures at most 1-bit change in the output. Is it correct?
I don't know.
Okay, but okay, these questions was actually discussed in last week also, so let me just clarify that for DES S box, basically 1-bit change to the input actually at most can affect 4-bit in the output. So if you remember how a DES is box is defined, DES is box is defined in form of a table, right? So the table has 4 rows, right? And there are 16 columns. So DS is box takes as input 6 input bits and outputs 4 output bit. Now among this 1 2 3 4 5 6 among these 6 input bits, first and last input bit together consist of the row number. So if your first and last bit are 0 0, so it goes to the first row. If 0 1, then second row, and so on. Sorry. Okay. And for the middle 4 bits, they together consist of the column number of the column number of this table representing DSS box construction. Now for example, if your DS input is 101011, then you, for the first and last bit being 11, you go to the third row of your DSS box table, and for this value 0101, that is 5, right? So you go to the fifth column of the S box. So you see the last row entry of fifth column, and whatever four binary digits. So there is a, because I said that output of DES box is 4 bit long, so each cell of this 4x16 table stores a 4 bit binary string representing the output of S box for that particular entry. So for this input 101011, you go to the third row of DSS box table and fifth column of DSS box table, and whatever the 4 bit binary string entry is present in that cell, that becomes the output of your DSS box. Now the way DSS box is designed in order to satisfy the avalanche property, so you change one bit in your input, and that will actually affect at most all the 4 bits of the output. So because in this question, in the statement it is written at most, so it is not 1, it is actually at least 4 bit to be changed in the output. Okay. And the last statement says AES block cipher has a 128 bit block length and uses 128 bit key. So basically, considering there are 2 more variants of AES for length of 192 bits and 256 bits, so we say that this statement is not correct. So basically first 2 statements are correct. Okay. Coming to second question. Consider the following encryption schemes. Which of the following options is or are true for the given encryption scheme? So there are 2 construction of encryption scheme are given in this question. You need to comment upon CPA security, CCA security of these schemes basically. So I think these were discussed in last week also. So anyone would like to answer one after another? So let's go with the first one first. So the encryption scheme is given as the first one. Your encryption algorithm for key K and message M, it outputs C1, R, where C1 is FKM XORed with R, and R is also present in the output. So this is your ciphertext format. Now you have to say whether this is CPA secure, CCA secure, anything.
Yeah, it is not CPA secure.
It is not CPA secure. Why?
Because for a fixed message, the FK of M value is fixed.
Correct.
And the adversary will be able to know this value. by knowing C1 XOR R.
Correct. So basically what adversary does is that there is this challenger and there is this adversary. It can in fact in the query phase query for message M0, and in the output it says that fk M0 XORed with R, R as corresponding ciphertext. Because it knows the value of R, it can XOR the value of R with the first part of the ciphertext, this C1 part, and it can get to know the value of fk M0. Now it can also query with M1 and get to see the ciphertext fk of M1 XORed with some R dash, and randomness are also returned as part of the ciphertext, and then it can recover the value of fk of M1 because it XORed the part R1 with the first part. Now in the challenge phase, so this is the query phase gets over, and in the challenge phase the adversary is supposed to send this same M0 M1 to the challenger, and challenger outputs ciphertext corresponding to any one of them. Now it will have the form of fk of MB XORed with some another R randomness, and so R double dash is the randomness used this time. Now this is returned. So again by XORing this R double dash part, the adversary can see the value of fk MB. Now it just matches whether this value is equal to this or this value is equal to this, and it can with probability 1 answer what is the bit B, that is which message was chosen for encryption M0 or M1. Thus CPA security is broken for this scheme. Now is this CCA secure? CPA security is broken, right? So is this CCA secure? Chosen ciphertext security is there. Will it be CCA secure?
This is just I'm thinking logically because I had the same question whether it is CCA secure or not. But can we give this reasoning that this is not CCA secure because the adversary can change one bit of C1 and one bit of R. So then also by if the adversary changes one bit of R of C and one bit of R.
So
Then
basically even so you are trying to devise an attack using the decryption oracle, right? But very basic point is that because it is not CPA secure, you don't even need the access to decryption oracle, right? So as we in the very earlier classes we saw that there are this concept of security starting from this eavesdropper thing, right? That is ciphertext only attack, and then so this is COA, ciphertext only attack, where the adversary just gets to see one single ciphertext and it has to guess the underlying message. And then comes KPA, where adversary has access to a table where some number of plaintext ciphertext pair are stored, but it has not control over which plaintext and its corresponding ciphertext it will see. Then comes CPA, that is chosen plaintext. So it can choose plaintext of its choice and can see the corresponding ciphertext by using the access to encryption oracle. And then comes the CCA security, chosen ciphertext attack, where apart from encryption oracle the adversary has access also to decryption oracle. So but in all these games the final let's leave this, but for these three I am leaving this because here you are just seeing one single okay even if I consider the first one also. So let's assume there are two message of adversary's choice M0 and M1. So this challenge phase is same for all the four cases, adversary's choice M0, M1 are given to challenger, and ciphertext corresponding to any one of them is returned, and adversary's job is to guess this bit P. Now this is the challenge phase, which is same for all the 4 cases, but what differs in these 4 are what extra information or extra advantage the adversary has, and that advantage grows in this direction. So CCA is the highest part where adversary has access to both encryption and decryption oracle. But the target it wants to achieve is to guess the bit B correctly with non-negligible probability. But that job is accomplished by exploiting the encryption oracle only, because it is not CPA secure. So only exploiting the encryption oracle access it is able to achieve this task. So it does not even need to use the decryption oracle, right? So because it is not CPA secure, we can directly say it will not be CCA secure. As simple as that.
But CC secure means changing the ciphertext and
Right, that is how we want to use the decryption oracle. What we try basically is that using the extra advantage of having access to decryption oracle, we try to tweak the challenge ciphertext basically such that there is some relation between the challenge ciphertext and the ciphertext that adversary chooses, and we try to exploit the relation between these two ciphertext to get reflected between the MB, the challenge message, and some MB dash, such that we can guess what MB was. So we try to find such information by looking at the decryption oracle service. But if you are able to do the same job, that is guessing the bit B using encryption oracle only, you don't even need to exploit decryption oracle. You are done already. So it will not be CCA secure. And what about the second one? So the first is neither CPA secure nor CCA secure. Done. What about the second one? This was also discussed, I think, last time. So the encryption scheme here is encryption dash, let's write with key K, message M returns ciphertext of this form, where C has this form F of Fk of R, right? So is this CPA secure?
yes, this is CPA secure
Right, but
because of the randomness that is.
right, so randomness
Randomness
is
that is
fed into the PRF. So even if the adversary knows the value of R, randomness R, it cannot exploit that value because the R is fed into the PRF, and PRF output is completely cannot be determined from its input, right? So it behaves as if it is a truly random function. So by seeing the input of the PRF, you cannot guess the output of the PRF, and so M getting XORed with such a PRF output value. So this basically helps to achieve CPA security, right? But it is not CCA secure, right? Why? So how basically the adversary can exploit the decryption oracle? So after seeing the challenge ciphertext,
Can we say like this is the this is not CCA secure because if the adversary changes one bit of C, then
Hmm.
the one bit at the message gets changed.
Correct.
So that is why the adversary is able to transfer the incorrect data in the way the adversary wants.
Correct. So let's say this is the challenge ciphertext that adversary has seen, and now it queries the decryption oracle with this C. So ciphertext has bit length. So C1 has bit length n only, right? Because it FK is a PRP. So it can XOR the C1, this R comma C, the C part, it can XOR with this string, keeping the last bit only 1. So basically XORing C with such a bit string will flip the last bit of the ciphertext C, and if it is given to the decryption oracle by the adversary, in response what it sees is basically this ciphertext. So that is challenge ciphertext with its least significant bit flipped, okay, and that gets XORed with this pseudo-random function output value, okay. Now whatever you get, that is nothing but the original message that was encrypted under the challenge ciphertext with its least significant bit flipped, right? So that is how you can exploit the decryption oracle service to get to know the information about MB with probability 1, okay. So this is your query ciphertext to decryption oracle if your challenge ciphertext is this, okay. So basically 2 is CPA secure but not CCA secure. So which of the following is or are incorrect? If adversary can derive a related ciphertext as a function of an existing ciphertext, then the scheme is not CCA secure. Is this true?
No, ma'am.
It is not true. Why?
So, ma'am, it is true.
It is true, right? It is true. That's what we were just now discussing, that if adversary is able to derive a related ciphertext as a function of existing ciphertext. So existing ciphertext means here the challenge ciphertext only, because we want to know the information about the underlying plaintext of challenge ciphertext. So if I am able to get some related ciphertext whose relation is also reflected upon the underlying plaintext also, then we can exploit that using the decryption oracle service, and then the scheme's CCA security is broken. So this statement is true. 3DES is widely recommended for use due to its high security to key length ratio. Is 3DES secure in present scenario? Is it recommended to be used? It is not, basically. So you can see in the lecture only that there is this meet in the middle attack concept, where you start from one direction, exploit all the possible keys here, and get to reach. So basically what is 3DS? So there is concept of 3 different key. So maybe you first encrypt with K1, decrypt with K2, encrypt with K3 with the message, something like this. So instead of, so as we said, the DES has only 56 bit key, which is very low. So we want to increase the key space. So instead of single 56 bit key, if we are trying to use 3 different 56 bit key, keeping the rest of the encryption operation, encryption and decryption same, and that is how you define 3DES. There are variants also. So anyway, we can say that due to this man in the middle attack concept, uh, so the key space is now 56 into 3, right? That is 168 bit long. So what we expect is that an adversary should not be able to gain any information about the plain text uh, we like not using less than 2 to the power 168 bit of number of operations or polynomial like. So this is basically your key space, and you don't want your adversary to be successfully break the system using lesser than this operation, but there is this meet in the middle attack concept with which you can show that actually the bit security comes down to 112 bit. So you exploit this side keys and this side keys, and final security that you achieve is 112 bit security, not 168 bit security. So 3DES is not recommended actually. So this is wrong. Third statement, in a CCA attack, the adversary can ask for decryptions of any ciphertext of its choice. Is it true?
No, it's false.
It's false, right? So the adversary is not allowed to query the decryption oracle with the challenge ciphertext. Except challenge ciphertext, it can query with any other ciphertext. So this is wrong. Chosen ciphertext attack is significant only from a theoretical point of view, since a decryption oracle is unrealistic in practice. Is it true?
I got this question wrong, this option, because I did not understand that it's written chosen cipher. It's the decryption oracle is unrealistic, but we have created decryption oracle because such
Yeah.
type of
So we were talking
exist.
about this last week also. So it is not unrealistic in practice, but it is not. So decryption oracle, it is not like that the company who are giving you the encryption service, they only provide to an adversary the decryption oracle service themselves. It's not like that, but somehow you can exploit some information and make this
Yes.
service available to you as an adversary. So it is not unrealistic. If it would have been unrealistic, then this CCA security concept would not have come up in the area of cryptography. We consider this CCA security concept because it is in real life possible to have access to some kind of decryption service. Okay. So it is not unrealistic. So that's why this statement is wrong. The theory comes in to the picture because there was practical scenario where it was possible. So you can see the lecture for some example from second October. That was interesting. It's in the book as well. So anyway, so first statement was correct. Right. Select the correct options with respect to message authentication code. The tag verification algorithm can be randomized or deterministic. Is it true? Tag verification algorithm?
This is false because the tag generation algorithm is randomized or deterministic.
Right.
Tag verification is deterministic.
Right. So this is false. Head of an organization sending a broadcast email to employees is an example application that requires encryption and not authentication. True or false?
This is false.
This is
It
false.
requires authentication.
Correct. So
It may require encryption or it may not.
right. Right. So okay, nothing to explain. You already answered. CBC MAC can be used to generate tag for variable length messages. It can be, right? So there are concept of padding and all. So it can of course be used to generate tag for variable length messages. So okay, this was wrong. This was wrong. This is true. Blockwise CBC MAC initialized with IV equal to, so with fixed IV the CBC MAC is getting initialized instead of IV being number of message block is insecure. This is also true. This also we discussed in the last week, right?
Ma'am, this can you explain the last one again? I did not understand the wording of the question actually.
So the CBC MAC, if you see, the
It
whole
has any IV value. Yes.
so the whole how the CBC MAC is constructed. So I would suggest that you just go through the whole construction once again in the lecture. Then you will understand that the IV being number of message blocks somehow it breaks this it is used to encode the message in such a way that the prefix free encoding is possible. So there is in the set of query messages in the message tag generation query, there is no uh, prefix free input, right? So to ensure that, it is required that you keep this as the part of the message, the length of the message. If you don't keep that, then it is it turns out to be insecure.
Okay.
Okay, consider a MAC construction for messages of length 2n using a secure PRFF. To authenticate a 2n bit message written as m equal to m1 concatenated with m2, where m1 and m2 are each n bit long, output a tag fk m1 fk of m2. So this is how your tag is generated. Now question is whether this construction is CMA secure. So chosen message attack, strong chosen message attack, CMA and SCMA. So I think this is easier. I would expect answer from you. Like similar question we discussed last week, how you can find a valid message tag pair for some unknown message, right? So can you find, basically my question is, can you find some m star t star for this particular tag generation algorithm such that your m star t star is a valid message tag pair for some unseen message m star. Unseen means for which you have not seen the corresponding tag yet. You can query with messages of its choice and then come up with some valid message tag pair. How you can do that here? You can use similar strategy just. So I think last week we had seen that if this is the case, so if I think we had seen construction like this, fkm2, if this is your tag for a message m1 concatenated to m2, then we said, so let's say for this example, what would have been the answer? What would have been a valid message tag pair that you can generate on your own? If this was just mk, if m1 comma fk m2, what would have been your m star t star? Anyone? Okay, so let me answer this first, then I will go to this. So for this, where tag is fkm1 comma fkm2, then what you can do m star equal to m2 concatenated with m1 and return tag as, you can see both this part separately, right? So bring the first second part as first part and send the first part back to the second part, and this is your m star t star, and it will be a valid message tag pair, right? So this is how you can construct. So your CMA security is broken basically. You see, you query with such an m1 concatenated with m2 and see the response, and then you generate message tag pair m star t star, where m star is m2 concatenated with m1 and t star is like this. So what about this? The only difference is instead of fkm2 it is written as fk of m2. 2 times this f has been applied to m2. Anyone would like to answer?
Ma'am, in
Yes.
this case, we can have three types of query. Two types of query. One
Okay.
is in message as M1 concatenated with M2,
Okay.
and then accordingly we'll get tags,
Hmm.
and the second we'll have M1, no sorry, M2 concatenated with say M3,
Right.
or and then in the final challenge phase, the adversary can send the tags for M1 concatenated with M3.
Very good. Right. Correct. So let's say the first one, I am writing the tag is t1 comma t2, where t1 is fkm1 and t2 is fk of m2, and this I am writing as say t1 dash t2 dash, where t1 is fk of m2 and t1 dash is fk of m2 and t2 dash is fk of m3. Now you are generating tag for m1 concatenated with m3, and you are returning tag as t1 comma t2 dash, right? So t1 is fk of m1 as desired from the construction of tag generation, and t2 dash is fk of m3. So this will be a valid message tag pair, correct? So this is not CMA. Yes.
Ma'am, one question I did not understand, that how do you differentiate whether it's a CMA or an SCMA? Because what I have understood is that SCMA is when the message is unique. Either one of them. But I did not understand that.
Right.
How do we differentiate if it's a CM?
So this security definition, the difference between CMA and SCMA case is that in CMA, let's say you have queried with a set of message mi, and you have seen the set of tags corresponding to mi's. So q number of queries you have done, and q number of corresponding tag you have seen through the query phase, and now you are asked, rather the adversary is asked to generate m star t star such that m star does not belong to this set of mi's, right? All the query messages that has been done and corresponding tag have been chosen, have been seen by the adversary. This is CMA game. So m star should not belong to the set of query messages. In case of SCMA, again you are querying some q number of messages and seeing the corresponding tags, and then you are the adversary is asked to submit m star t star, where this whole pair m star t star should not belong to mi comma ti pair for any of the query phase message tag pair. Difference being, this is very much related to deterministic MAC, where for same mi, ti is always fixed because it is deterministic MAC. For the same mi, you will always get same ti. So if you allow m star to be equal to sum of the query message mi, then you already know its corresponding ti. So you cannot return a valid message tag pair of your own. You will trivially win the game if you allow m star to be equal to any of the query messages, because you already have seen the response ti. So there is no meaning to allow the m star to be equal to mi. This is the case of deterministic MAC. Now for randomized MAC, for same mi, there can be several ti values possible because it is randomized. So if you are querying mi several times, each time you can get some different value of its corresponding tag. So here we say that the adversary is asked to generate m star t star such that m star t star has not been seen as a valid message tag pair in the query phase already. So it has to come up with a new. So m star can belong to any one of such message mi, but the corresponding t star should not be equal to the tag already seen by the adversary. Even if it has seen, say for m1 it has seen some t1 as the valid tag. Now if it is trying to response with m1, then it has to be some t1 dash such that t1 dash and t1 is not same. Although the message part can be same, in the SCMA game its corresponding tag part should not be same as already seen by the adversary, right? So that is why we take the whole message tag pair and then say it should not belong to the already seen message tag pair. That is the difference in case of am I clear?
Yes, ma'am. So in this case, in such type of questions, so first we will have to identify whether it's a randomized algorithm,
Right,
randomized tag generation algorithm or deterministic.
right. If
Then
you find
we
it,
should go ahead.
continue.
Then we should go ahead and see whether it's then if it is a, like in this particular question, it is a deterministic, right? So we can be 100% sure that SCMA it will be there. If CMA is there, SCMA will be there.
Right, right. For deterministic MAC, if it is CMA secure, that will only imply it is SCMA secure also.
So in this particular question, because it is deterministic, so if it is not CMA secure, it will not be SCMA.
Right. This is just same as if it is not CPA secure, it will not be CCA secure. Similar to that, if it is not CMA secure, it will not be SCMA secure.
Yes.
Okay. Now this week's topics. Select the correct statement from the following. Perfect secrecy implies zero winning probability of an adversary. Is it true? So perfect secrecy is week 1 concept, right? Do you remember perfect secrecy? Perfect secrecy implies
It's true.
it's true, right? So perfect secrecy is against unbounded adversary, computationally unbounded adversary, and the winning probability is exactly 0. Information theoretic security implies zero winning probability of an adversary. So this concept came into week 6 for information theoretic secure MAC concept. Now in general, information theoretic security, is it true or false? It is false. Okay, information theoretic security actually allows the adversary to win with very small, like negligible probability. It's not 0. Okay, information theoretically allows computationally unbounded adversary to win with negligible probability. Okay, so this statement is wrong. Perfect secrecy is achieved in presence of computationally unbounded adversary. Yes, it is true, as already said. And information theoretic security is achieved in presence of computationally unbounded adversary. This is also true. Okay. Only incorrect was the second option. Select the correct statements. So there is this concept of ideal cipher model introduced, right? So you have to say, in ideal cipher model, the adversary is assumed to be unaware of the internal computation of block cipher. Is it true? So anyone would answer this?
Yes, it's true.
It's true. Correct. It is true. Second one, in ideal cipher model, the adversary can use block cipher as oracle service and query the oracle in two ways. This is also true because the adversary can query the block cipher as oracle service in two ways. That is, it can query for the block cipher f or its inverse function f inverse. Okay, in both way it can query the ideal cipher model. Davis-Meyer construction of fixed length compression function is collision resistant in ideal cipher model. Okay, this is also true. So in the lecture it is in detail explained that why do we need the ideal cipher model for this particular Davis-Meyer construction. So if you remember from the lecture, so we use this construction for fixed length compression function, right? Yes. So we define something like this, that there is the function like this, where there is this block cipher. So basically each takes as input both m and t, and you apply block cipher by using the message block m as the key and pass the input t to the block cipher and then XOR it with t. So this is how your Davis-Meyer construction is defined, and it is shown that if this service, the internal construction of this block cipher f is assumed to be hidden from an adversary. So usually in cryptography we assume that any cipher algorithm, so any encryption algorithm, decryption algorithm, all the algorithms are public. It is usually assumed, but in ideal cipher model we just assume this block cipher f to serve as some truly random function. Okay, and this is needed such that you can query with input x and say input ki, and you get to see the value of fki xi, or there is another oracle which serves as f inverse. There you can query with some ki and yi, and you get to see f inverse of yi for key ki, and these two are served as oracle service. Why oracle service? Because it is assumed how exactly the algorithm inside f runs, that is not known to the adversary. It is an assumption, and using this assumption we can show the proof of security for Davis-Meyer construction, that indeed this fixed length compression function is collision resistant, and if such a collision resistant fixed length compression function is there in our hand, then using that using the Merkle-Damgard construction we can get arbitrary length collision resistant hash function. Okay. This fixed length collision resistant compression function is building block for Merkle-Damgard construction of collision resistant hash function, and to achieve fixed length collision resistant compression function we make use of this Davis-Meyer construction, which is proven to be collision resistant assuming this ideal cipher model, where the internal computation of block cipher is assumed to be hidden from the adversary, and adversary can only see the result of computation of f and f inverse, that is block cipher and inverse of block cipher, by using it as an oracle service. It cannot itself evaluate it. These are assumptions. Okay.
Ma'am, one question from previous question, problem number 1. I had one. From problem number 1, previous slide.
Okay.
Ma'am, in this, like over the period of so many weeks of lectures that we have taken. So here we came across three terms. One is perfect secrecy,
Correct.
one is information theoretic security, and another is computational
Correct.
secrecy or security. So why we have all these three terms? Just to differentiate between a computationally bounded adversary and
Hmm.
bounded adversary.
Yes,
So
you have.
why not just one term or two term just to differentiate?
So you have already answered, right? So in all the cases, adversaries' power are different. Like in perfect secrecy, adversary is computationally unbounded, and
Hmm.
we do not allow the adversary to even win with negligible probability. In other words,
Okay.
adversary will win with zero probability in perfect secret world. In information theoretic security, we say that adversary has unbounded power, but we allow a negligible probability with which it can win. And then in computational world, the adversary has limited computational power, or it is bounded, computationally bounded adversary, and also it has negligible probability of winning. So
So
the
when do we
restriction.
use which one?
So uh, as you will see more and more primitives, crypto primitives. So you have already seen for encryption decryption we are usually in computationally secure world.
Computation security.
But then when constructing Mac, we saw that we are trying to achieve some Mac which will be information theoretic secure against some bounded number of queries. Okay, so as you have seen that one time information secure information theoretic secure Mac, or
Yes.
L time information theoretic secure Mac, where you allow the adversary to query for at max L number of messages and see the corresponding tag, and then the adversary has to come up with valid message tag pair. So this L is some constant. Now so
Hmm.
basically, depending on always in any case, our target will be to achieve security against computationally unbounded adversary, and we will
Yes.
allow, we want that adversary has zero winning probability. That is the perfect world, but this is of course hard to achieve, or impossible to achieve, next to impossible we should say. So we got into the computational world. Then when seeing Mac, we saw that okay, researchers are trying to uh, achieve something in between, where it will assume that let's assume that adversary has unbounded computational power, and still, except negligible probability, it will not be able to attack the system. So we have achieved something better than computational secrecy world in case of Mac. So it varies with crypto primitives.
But in case of encryption, decryption schemes, encryption schemes, we are not able to achieve that
Right,
with computationally unbounded adversary, right?
right, right,
And one more thing, like in information theoretic, the probability is like I think that there's an epsilon that is mentioned. But in
right.
computational security, I found it's a negligible probability, that negligible function that we used.
Okay,
So
so
we are using
it,
two different.
it is just about notation use. Okay, so uh, when you write negligible of some security parameter, and epsilon is also some small quantity. So how small, that depends upon, like as you have seen that, let's say you are using some group ZP for your one time secure IT Mac, information theoretic secure Mac, and then you are computing the probability of winning to be 1 by size of ZP square. So size of ZP is P, right? The group ZP has size P. Now if P is a large prime, then P square will even be larger, and 1 by P square will be very small, but there is no n involved directly. So this is also small quantity, and negligible function has certain definition as we had seen earlier. So finally, what we try to achieve, that adversary has very small probability of winning, whether it is written in terms of the security parameter n, or it is just written some random epsilon. It is just about notation. Okay, select the correct statements. SUF is a special case of L-wise independent function. SUF is a pairwise independent function. Knowing the output of SUF for one input, it is hard to guess the output on a new input. You can quickly answer the question. I will not take much time on this. SUF is strongly universal function. Okay, so how do we define SUF? It is the, so we say that for two message M1 and M2, your function output should not be affected by the relation between M1 and M2. So it is similar to the idea of pseudo-random function, but in case of pseudo-random function, you allow the adversary to see some polynomial number of input-output pair, and then the adversary has to decide whether it is interacting with a truly random function or pseudo-random function. In case of SUF, we are saying that you can see just let's say one input-output pair, and then you can think of this way, then you have to say whether the another pair of input-output second time that you are seeing, whether it is a function output or not. You can think it in that way. Or in other words, the SUF output on some input M1 is independent, completely independent and uniformly distributed over the output space, and so your output on some message M1 and some message M2, they are completely independent of each other, and they can lie over uniformly randomly over all the output space. Okay, so because we are just talking about independence between the outputs of two corresponding inputs, so this is pairwise independent function, and it is of course special case of L-wise independent function. If we would have been allowed independence for 3 input-output pair, then it would have been 3-wise independent function and so on. So it is a special case of L-wise independent function. And knowing the output of SUF for one input, it is hard to guess the output on a new input. This is also true. You can guess the output only with probability 1 by tau, okay, where tau is the output space. So all of them are correct. This is a simple question about the definition of group and fields. I will read out. Select the correct statements. A group with certain binary operations satisfies closure property along with associativity, presence of identity element, and existence of inverse for each element in the group. Is this true?
Yes, true.
Yes, true, right? So this is just the abstract algebra concept. An abelian group is a group with commutativity. This is also true, right?
Yes.
So basically, just to recap once, so a set G with some binary operation denoted with, say, this dot operation, we say this is a group if these properties are satisfied. First one is closure property. That means in this set, for any two element A and B belonging to this set, if A dot B, this also belongs to the same set G, then we say that closure property is satisfied. Presence of identity element, that means there must be some element, let's say E, in this group G, such that for any element A belonging to G, A dot E gives back A, and then there is this for every element A belonging to G, there has to be another element B such that A dot B gives you the identity element E, and then we say B as the inverse element of A, and then comes the associativity property, which says that for any ABC belonging to G, in whatever order you apply this dot operation, whether it is A dot B then dot C, or it is A dot B dot C, both the results are same and of course belongs to G. So these four properties if satisfied, we say that this set G along with this binary operation dot is a group. And if this group additionally satisfies another property of A dot B being equal to B dot A, then we say this is a commutative group, and this is also called abelian group. And in case of field, this is another abstract algebra structure where instead of one single operation there are usually two operations defined. So a set F is there and two operations are defined such that F is a group with respect to this plus operation. So this is just a notation. How you exactly define this operation depends on the set F. So F along with this operation plus, this is the abelian group. F except the identity element of this abelian group with respect to operation plus, let's say this is the identity element denoted with 0. So if you exclude this 0, this identity element of plus operation, and this group excluding this 0 element is abelian group with respect to multiplication operation, and multiplication is distributed over addition, that is A into B plus C is A dot B plus A dot C. This is, we call that multiplication is distributive over addition. If these properties are satisfied, then we say that the set F with these two binary operations are is called a field. Okay, so yes, the statements are correct. Quickly you can answer this question very quickly. R is the real number set. Is it a group with respect to multiplication operation? So you have to check whether it satisfies closure property, associativity property, presence of identity element, and existence of inverse for each of the element. Real number set with respect to multiplication. Anyone?
Yes, this is a group.
This is a group, right? So the identity element is for multiplication with any real number. The identity element is 1, right? And for any real number, let's say if we have the real number represented as 2 by 3, then we will get 3 by 2 as inverse of it, okay, such that their multiplication gives back 1. So with respect to multiplication, it is a group. Two real numbers multiplied always gives back real number. So what about the next one? R excluding 0 element and plus, is it a group? it is not right, because for addition operation identity element 0 has to be there, otherwise for any real number you add it to 0 and you get back the same number. So 0 is the additive identity. If you exclude 0 for the addition operation, it will not be anymore a group. So okay, what about z excluded 0 and plus? It is a abelian group,
No, it's not an abelian.
right? Because
Right.
if additive identity element 0 is excluded, so it will not be group first of all, and of course not abelian. And what about r excluded 0 with multiplication?
This is also a group.
So okay, I was wrong about the first statement, because 1 minute. So there is no inverse element of 0, right? For the first statement, r along with multiplication, this will not be a group because there is 0 present and there is no inverse element of 0. You cannot divide 1 with 0, right? So because 0 has no inverse in the first statement, this is wrong. So r excluded 0 along with the multiplication operation, that will form a group. So last statement is correct, not the first one, and second and third are also not correct. Am I clear? Now there is some problem to solve. You have to prove the given function is strongly universal function, SUF. So this is defined as, you have this key space over zp to the power l plus 1, that is your key has l plus 1 elements, each coming from the set zp. Zp is 0 to p minus 1, okay, modulo p set, and you have l plus 1 elements from zp, that is your key space, and your message space is l number of elements from zp, and then you generate this, let's say, tag. So the output space t is one single element of zp, and you define a function h from k cross m to t such that h along with this key, this is l plus 1 number of zp element, and takes as input l number of zp element as message, and outputs this k0 plus kimi dot product. Basically you perform k1 m1 plus k2 m2 till kl ml mod p. So the final output is the modulo p, so element of zp, and you have to prove that h is strongly universal function. So let's remind once that what is strong universal function. So for strong universal function, basically what you have to show is that probability of h with some key k for a message m0 generating the output as t0, and hk m1 outputting t1 together satisfies, this probability should be 1 over the output space size square. This is the condition for this function being strongly universal function. This is the output space. So together these two are satisfied for some value of m0 m1 and t0 t1. This should be 1 by t square, size of t square. So how can you prove that? So maybe I can give you some hint. So you can, how can you expand this thing? So M0 is basically, M0 itself has L number of ZP element in it, the way the input of function h has been defined, and k has L plus 1 parts in it. Okay, so hk of M0, let's write it as k0 plus k1 M01 plus k2 M02 till kl M0l mod p. This is your T0, and your T1 is hk M1 written as k0 k1 M11 k2 M12 till kl M1l mod p, right? Now you have to find the probability of both of these being true, right? Both of these hold. With how much probability? Alternatively, you can see, you can just subtract the second line from the first line, so you get T0 minus T1, K0 and K0 gets cancelled, so you get K1 M01 minus M11, K2 M02 minus M12, and so on, KL M0L minus M1L, all in modulo P. Now see that with so total key space here, that is L plus 1 number of elements from ZP, right? So this is, there are for each of the L plus 1 elements in K, you have P probabilities to fill up that number, right? So your key has like this, total L number of elements, okay? And each of this space can be filled up with P varieties because the elements are from ZP. So 0 to P minus 1, all the P options are possible to fill up each of these positions. So in P to the power L plus 1 ways, you can generate a key. So total key space size is this. Now here you can see that, let's assume there is some index I star between 1 to L, for which M0 I star, okay, I star ith element of M0 is not equal to I star ith element of M1, okay. This is the highest point where this mismatch occurs, okay. So above I star, for all the i's which lie after I star till L, for them actually M0I is equal to M1I, right? M0I is equal to M1I. Am I clear in this? If I star is the highest index position for which the I started element of M0 and I started element of M1 differs, then above I star, all the I position till L, all of them has same entry at their ith index. Am I clear in this? Total L number of positions we are considering, okay. Among L number of position, I am saying that, I am just assuming that I star is the highest index position for which M1 and M0 differs. So after I star, all the positions till Lth position, M0I and M1I will be same. So m0i minus m1i will be 0 after I star. So what is left with is that if I write ki m0i minus m1i, okay, this is for, so we take the summation for I1 to I star minus 1, okay. So for all the position below I star I am taking the summation, and also for the I starth position itself I am writing ki star m0i star minus m1i star. This will certainly not be 0 because I am assuming that for the I starth position m0 and m1 entry differs. So this is certainly not 0, and here we don't know, so any combination can be possible. Now let's say that, so in this equation, that is t0 minus t1 equal to summation of ki into m0i minus m1i for the I value starting from 1 to I star minus 1 plus ki star m0i star minus m1i star, and for the rest of the index above I star, because m0i and m1i are same, so these entries become 0, so only this much case is considered. Now in this equation we know the value of tags t0 and t1 value are known, and the message value are also known, right? We assume that we know the value of m0 t0 m1 t1, and we want to find the probability with which this can be true, that t0 is a valid output result of function h and t1 is a valid output result of input m1 with respect to key k. Now we are trying to get that probability. So if we fill up this I star minus 1 number of ki values of our own choice, so you do ki, you assign random value from zp to all the ki's for I in the range 1 to I star minus 1. So this I star minus 1 number of positions in ki are arbitrarily filled up. So if you fill up those positions, so you can compute this with those particular values, and you can get to know the unique value of ki star. Why unique? Because with those assumed I star minus 1 number of ki positions with the known values, you can compute this in zp, and then you can subtract that value from t0 minus t1, again you get a zp element in this side, and then you can compute ki star equal to the value this side into m0i star minus m1i star inverse, okay. Because p is a prime, so zp, each element of zp can be inverted, so this element m0i star minus m1i star will also have inverse. So you can uniquely compute the value of ki star. So what we see is that with this I star minus 1 number of values arbitrarily assigned to it, you can get unique value of ki star, and once you know the value of ki star, and with your own value of k1 to ki star minus 1, you can get the value of k0. You just put the values in this equation and get the value of k0, right? So basically you are allowed to choose random values for the position I to I star minus 1, and then your value k0 and ki star gets known. So in the worst case, I star can be the last position, that is the lth position. In that case you can randomly assign values to all l minus 1 position, and then get unique value at 0th position and lth position. So now the key space you can choose actually is 2 to the power l minus 1. So although p to the power each point can have p possible values. So you can arbitrarily choose l minus 1th number of positions, and then rest 2 position gets determined automatically. So this probability is actually p to the, so this gets down as p to the power l minus 1, right? And your whole key space has the size p to the power l plus 1, and this gives you 1 by p square. This is nothing but the output space square. So with this probability this event can occur. That is why we can say that H is strongly universal. Am I clear? Hello? Hello?
Yes, ma'am. We are good.
Okay. So that is how you can show that a given function is strongly universal. Now the next question also is in the same line actually. You can follow the same approach to prove. So this question also asks to prove that H is strongly universal. So just basically here you have two part of the keys written as k comma v, and your input is m and output is k into m XORed with v. All the entries are from 0 and 1. So in the last question all the entries were from ZP. Here all the entries from 0 or 1, and key has two parts, where the first part is actually binary matrix of dimension L cross n. Okay, this is the k part. So you are basically multiplying a L cross n matrix with your n bit message. Message page is given as binary of size n. So your message has dimension n, so you are multiplying this matrix k with your message and then XORing the output with v, which has dimension l. So this is the v part of the key, last part of the key. Now here also, if you have to prove that H is strongly universal, again what you do is that you do the probability of H kv of m0 being t0 and H kv m1 outputting t1. What is the probability? Ideally what you want is that because your output space t has the size of l, so it is l bit binary string, right? So you want this to be this, right? And okay, let's see. Now to prove this, we can expand again as before. T0 is k m0 plus v and t1 is k m1 plus v. If you subtract, you get t0 minus t1 is k m0 minus m1. V gets cancelled. Now m0 and m1 are n-dimensional vector and k is l cross 1 matrix, and t0 minus t1 are also vectors, right? L-dimensional vectors. Now how we can like with how many probability we can choose or in how many ways we can choose some, or we can fix some bits of the matrix K such that rest of the bits gets determined automatically, and these conditions also satisfies. Okay, so again we will take the similar approach actually. So K is a L cross 1 matrix and M0 minus M1 is a n dimensional vector. Now again we assume that I star is the highest position. So 1 to n, I star is the highest position where M0 and M1 differs. Differs means because both M0 and M1 are 0, 1 entries, so M0 minus M1 will be 1 basically. It will be 1. If it either they can be both 0 and 0 or 1 and 1, then the difference is 0, but because we assumed I star is the highest position where M0 and M1 differs, then M0 minus M1 must be 1. Okay. Now now notice that we can basically assign, where did the cursor go? Yes, so how matrix vector operation, so there is this I star and there will be there in column. So let's say here is the I starth column. Okay, now if you multiply, so this row gets inner product in this order, so these n elements are inner producted with these n elements. Now if I star is the element where the entry is 1, then if you basically fix this side of the entries in the matrix, so you fix all the I star minus 1th leftmost entry for all the L rows, then you can uniquely determine the ith column of matrix K. Why? Because for each row, if you observe, after I star all the differences 0, right? They are all 0. At I star position, this has 1. M0 minus M1 has entry 1. All the other entries are also known to you because you know the value of M0, you know the value of M1, you know the values of T0 and T1. So this part value is known. You have assigned values to this leftmost I star minus 1 entries for all the rows. Now you multiply this element, so you have randomly assigned these 0, 1 values to this position, right? Now after assigning, you multiply this with this with this, as the way you do matrix vector multiplication. Now this part multiplied with this part is already computed, and rest remains this multiplied with 1. So you can determine the value of I starth column entry for each row in this manner. So you fix the entries of I star minus 1 number of leftmost columns and you uniquely determine the I starth column. And at max I star can have value L. So I star can be last column also. So in that case, all the n minus 1 columns for the matrix K you have to randomly assign, and then only you can get to know the you can uniquely get the value of I starth column, which is nth column in this case. So there are total L number of rows are there, and you are randomly assigning values to n minus 1 columns. So total L into n minus 1 elements you have to assign randomly. So the probability is 2 to the power L into n minus 1, and also the vector v is also there as part of key, and vector v has size L. So 2 to the power L. So basically, if you get to know the value of I starth column, then you can determine the value of v by putting these all the column values in this equation. Then v also can be uniquely determined. The I star column can also be determined uniquely and v also can be determined uniquely. But the overall key space is 2 to the power nl, that is for the matrix, and 2 to the power l for the vector, right? So this is 2 to the power nl plus l, and if this is the possibility that you with which you can uniquely get this condition satisfies, then the fraction probability becomes ln minus 1 this by the size of total key space, which is nl plus l. So what you get basically, this is ln minus l and this is ln plus l, that gives you 1 by 2 to the power 2l. This can be written as 2 to the power l square, and 2 to the power l is nothing but the size of the space t, because t is l bit length binary string, so there are 2 to the power l possibilities of this tag space. So this is 1 over size of t square. So that is how you prove that this is also strongly universal. Is this okay? Okay, hope this is clear. So this is also another similar type of question. I think I should leave it for you because they are pretty similar. Here also your key has two parts, a matrix and a vector. As you can see, K is the matrix, V is the vector. Only difference is that instead of arbitrarily random 0, 1 values, the matrix has a particular form which is called Toeplitz matrix. The property being that a ijth element is exactly same as a I minus 1 j minus 1th element, which means if you have some specific value here, so this is 1 comma 1 entry, then 2 comma 2 entry is also same, 3 comma 3 entry is also same, and so on. So all these diagonal elements are same. If here 1 comma 2 position, here some entry is fixed, then 2 comma 3 position, 3 comma 4 position, and so on, all these entries are fixed again. So basically Toeplitz matrix is something where all the diagonals contain same value, okay, like this. Now exploiting this property, you can show that this particular function h defined in this way, so the same function was there in the previous problem also, with the only difference that the matrix pattern is different here, and you can verify whether again you have to fix some random values first, and then you see that how you can uniquely determine the rest of the part of the key, and similarly you can find the probability of h of m0 being t0 and h of m1 being t1. I am leaving this. Okay. So define an appropriate notion of a 2-time epsilon secure map and give a construction that meets your definition. So you in the lecture you have seen one-time secure, one-time IT secure map or some particular value epsilon secure map, where epsilon is the upper bound of winning probability in the game. Instead of one time, if you are saying that I am trying to build 2-time epsilon secure map, so you have to give a construction for that. So what will necessarily be the concept of 2 time epsilon secure math? For one time the game is like this. So here is challenger, here is adversary. For one time what you do is that you give some message, you see the corresponding tag, and then you have to come up with m star t star, right? For 2 time secure math, what will be the security game? Here you are like adversary squaring with m1, see the response t1, query with m2, see the response t2, and after seeing just 2 responses to messages of its choice, then it has to output m star t star, which has to be. And winning probability, so probability adversary wins is upper bounded by epsilon. Here also you want probability that adversary wins is upper bounded by epsilon. Now this is the security game that we want to satisfy, and now you have to give a construction of this. Some naive idea. So one example of IT secure math was given in this way, right? A comma b m plus b. This was an example, right? So this is like a straight line. Depending on your value of input m, you get the y value of that point on the straight line, right? So in the similar manner you can give twice epsilon secure math. Okay. So this can be a possible construction. So instead of a comma b, I can write a comma b comma c, right, of m, and instead of a linear function or straight line equation, I have degree 2 equation where I am writing am square plus bm plus c. This is analogously extended. Previously for one time secure math I had 2 part of the keys and I wrote am plus b. This is degree 1 function, this is degree 2 function. I have 3 part of the keys because I want 2 times security, and the function is am square plus bm plus c. Are you convinced that this will work? And of course a, b, c were as here also a, b, c are each of them are element of zp, right, for some prime p. And now, like, for showing that this is actually 2 times secure math, you have to prove this, right? Probability of hk of m1 t1 is t1 and hk of m2 is t2 and hk of m3 is t3, and this holds with probability 1 by size of t cube. In case of one time IT secure math, it was this probability of hk m1 equal to t1 and hk of m2 being equal to t2. That probability was 1 over t square, and here this becomes 1 over t cube for 2 times secure math. This is very naturally extended. Okay. For the next question, read it carefully. So let pi1 equal to tag gen1 tag verify 1 is a MAC system, and pi2 is another MAC system with the tag generation and tag verification algorithm over key space 01 to the power n. Now the key generation algorithm for both pi1 and pi2 outputs a random key from the key space. It is given that either pi1 or pi2 is a secure MAC, but which one, that is not known. So which of the following is or are true? So first, given pi1 and pi2, you are constructing another MAC pi, where the tag generation algorithm is defined as taggen 1. So taggen algorithm of pi1 using the part of the key k1 applying on the message m, and the second part is taggen to k2m. So in both the question, if you follow, the tag generation algorithm is exactly same. So in the modified construction pi, the key has 2n bit length. Okay. For individual construction pi1 and pi2, the key space was n bit binary string. For the modified max string pi, the key space is 2n bit length string written as k1 concatenated with k2. Now tag generation is same in both the cases. So T is written as taggen 1 with key k on message m, comma taggen 2 with key k2, this is k1, on m. So this is your overall tag for modified algorithm, which is same in both the cases, but tag verification algorithm differs. In the first case, tag verify is defined as m comma sigma 1 equal to 1. So if sigma 1 is a valid tag of m1 with respect to tag verification algorithm of pi1, and if sigma 2 is a valid tag for message m with respect to tag verification algorithm of pi2. So they are connected with AND statement. In the second case, tag verify is defined in such a manner that again it will verify whether sigma 1 is a valid tag for m with respect to pi1, or sigma 2 is valid tag for m with respect to pi2. So here this is AND, here this is OR, and you know that any one of them is not secure MAC. So a MAC is not secure means an adversary is able to come up with a valid message tag pair, right? So we want to know in which case pi is secure or not secure. So for the first one or for the second one, we need to comment on the CMA security of the modified construction pi. Anyone would like to answer? 2 minutes. You can think on your own whether AND one is secure or OR one is secure, when it is given that any one of them is not secure. Among pi1 and pi2, any one of them is not secure, then pi remains secure in which of the cases, where tag verification does the AND operation or the OR operation. Anyone would like to answer?
Ma'am, in this case, the AND one should be secure, because if either one of the like tag if either one of them is insecure, then in case of the first scheme, map, then in that case, the secure one will output as 0. If the tag has got more, if there is if
Yes,
the
yes.
adversary has created a
Right.
incorrect tag, but
So
in the
yes,
second
yes.
case it may give
So you are
a
correct.
for an
You are correct. So basically, your answer is correct. So because we don't know which one is insecure, so let's assume that pi1 is insecure. Then adversary should be able to come up with some m star comma sigma star 1 pair, right, which will be a valid message tag pair. Now if we consider the second case where the tag verification of pi checks that if sigma 1 is a valid tag for m, so this check will pass, right, because sigma 1 star is indeed a valid tag for m star, because we know pi 1 is insecure, so this can adversary can come up with such a pair and this will pass, right. So this part will output 1 and 1 is odd with some value, be it 0 or 1, but the tag verification will pass here in the second case. So although pi 1 is so because pi 1 is insecure, but due to this OR condition your tag verification will pass, right, in the second case, but in the first case it will prevent to verify the tag. Although for first one it is easy to generate such m star sigma star 1 pair, but it will not get passed by, so it will not get verified as a valid tag because it will be prevented by the AND condition. So it is not easy to come up with message comma sigma 2 star because pi 2 is still secure. If any one of them remains secure, then the first construction will make the tag verify work in proper way. Okay, your answer was correct. Select the incorrect options for the Markle-Damgard transformation. It employs a multi-stage approach and used in many popular hash algorithms like MD5, SHA-256. Is it true?
This is true.
It is true, right? This construction will always add a padding to the message which depends upon the length of the message. Is it true?
Yes,
Yes, correct, right? So at last always so if yes,
yes,
someone is saying something. Okay, so if you remember that in Markle-Damgard transformation the message is usually divided into some fixed length blocks, let's say L bit length blocks. Then even if your message is not a proper multiple of L or it is a multiple of L, still one padding block is always there which contains the information about the length of the message. So this is true actually. So the initial vector IV used in this construction can be randomized. So in Markle-Damgard transformation IV is fixed or it is randomized?
IV is fixed.
IV is fixed, right? So this is wrong. This is true. This is true. Transformation is a deterministic function of the input. So this basically finally construct a hash function, right? So this is of course deterministic. So incorrect option is the IV thing. Here comes collision resistant hash function. H is given as collision resistant hash function, then which of the following is or are false? The function h1x equal to hx concatenated with hx is not good. So okay, I will wait for your answer. So there are two constructions given. Two constructions are there. One is h1x equal to hx concatenated with hx. Another one is h2x 1 concatenated with hx. Comment on the collision resistance of h1 and h2. What do you think? So do you remember what collision resistance is? So I think I should just briefly recap that in case of in case of hash function. So there is challenger, there is adversary. Adversary's job is to come up with two such message or input, not message, two input, x and x dash, and it wins the game if h of x is equal to h of x dash, and adversary is able to output such message pair. These are collision pairs, right? Because the output collides, h of x and h of x dash maps to the same output, so they are colliding pair, and if adversary is able to output such colliding pair with non-negligible probability, then we say that h is not collision resistant. Now h is given as collision resistant. What about h1? Is it collision resistant or not? Any thoughts? Okay. So this will be collision resistant. So we can prove this by contradiction. So let's assume that h1 is not collision resistant. Then what happens? Then adversary is able to output x and x dash such that h1 of x and h1 of x dash is same. Okay. If this is an easy task to do, then this will imply basically by construction h1 of x is nothing but h of x concatenated with h of x equal to h of x dash concatenated with h of x dash. So you can clearly separate the first and second half of the output here also, and necessarily this will imply that you are getting hx and hx dash such that hx is equal to h of x dash, which means that h is not collision resistant, or in other words, if there exists an adversary who is able to break the collision resistance of h1, then we can use that adversary to break the collision resistance of h. But we already know that h is a collision resistant hash function, so we can say that h1 is also collision resistant. What about h2? Now you can answer similarly. Quickly, any thought?
H2 will also be collision
Correct.
resistant with the
Correct.
same logic.
With the same logic, right? Because if h2, we can find some x dash for which h2 of x and h2 x dash are same. Then 1 concatenated with hx is equal to 1 concatenated with hx dash, and this part are same, so that will imply that hx is equal to h of x dash. So it is easy to come up with x and x dash such that h of x is equal to h of x dash, but we will already know that h is collision resistant, so this is not true. Okay. Let f be a keyed function, so n bit key, n bit input and n bit output, and let h taking, so m is given as binary string of length upper bounded by l. Okay, so h takes as input any string of length at max l and maps it to n bit binary string. So h is a hash function. Now it says that consider the keyed function f dash, which takes as key n bit binary string and message as any binary string of length at most l, and outputs a n bit binary string such that f dash k of m is equal to f k of h of m. Then which of the following is or are true? If f is a secure PRF, then f dash is a secure PRF. If h is collision resistant, then f dash is secure PRF. If f is a secure PRF and h is collision resistant, then f dash is secure And last statement says even if F is secure and H is collision resistant, F dash need not be secure pair. So basically you have to comment on the security of proposed construction of PRF F dash. What about the security of F dash as a PRF? You have to comment on that. Depending on whether F is a secure PRF, whether H is a collision resistant hash function. What do you think? Anyone? FK, sorry. F dash K. Yes, anyone?
Ma'am, in this case, I think the function f dash to be called as secure PRF should have both. F should be secure PRF and H should be collision resistant. Because
Yes.
if H is collision resistant, then for two different messages M1 and M2, the value that goes inside the FK will be different, and so the final output of F dash will be different, and so the adversary will not be able to distinguish between the two messages.
Yes, yes, yes. Your answer is correct. Nice. Right. So just F being secure does not work, because in that case, even if F is secure, if H is not, so what you can do to break the security of F dash, if F is secure but H is not collision resistant, you can do that. H is not collision resistant, so you are able to come up with two such message M and M dash, for which H of M is equal to H of M dash. You can do that because H is not collision resistant. Then you query the oracle with M, and your output will be either Fk of H of M or some random thing, depending on whether you are interacting with TRF or PRF. And you query with M dash also, and your output will be either Fk of H of M dash or some other Y dash. Now if you are interacting with a PRF, then these two values will be same, and by observing that you can easily determine whether you are interacting with a truly random function or pseudo random function. So F dash security will be broken. If H is collision resistant but F is not secure, then of course it will not be secure, because the outward function F, if it is not secure, then F dash cannot be anyway secure. But if both the security holds, F is a secure PRF and H is collision resistant, then F dash will be a secure PRF, as correctly pointed out by you only. So okay, third option is correct. And this is the last one, I think. Let gen 1 h1 and gen 2 h2 be two hash functions. Define gen h so that gen runs gen 1 and gen 2 to obtain keys s1 and h2. Then define h of s1 s2 of x, h1 of s. Okay, so let me just write it. I think you can answer this also on your own. So h s1 h2 x is given, h1 s1 x, h2 x. So whether H is collision resistant or not. When at least one of H1 and H2 is given to be collision resistant. So you have to prove, basically it is already said that if at least one of these two, H1 and H2, is collision resistant, then H will also be collision resistant. You have to prove this. So I think in the same manner we can prove that if this is not collision resistant, then H of S1 S2 of X, you will find some X dash such that this holds, and this in turn implies that H1 S1 X h2 s2 x is equal to h1 s1 x dash h2 s2 x dash. And because any one of them is collision resistant, like this will imply the first half and this first half are same, that will imply that h1 is not collision resistant, and this second half and this second half are same, that will imply that h2 is not collision resistant. So basically gen h will not be collision resistant if both h1 and h2 are not collision resistant. If any one of them is collision resistant, then h will also be collision resistant by contradiction. Okay. Last one. I think you can answer same manner. So h is x is hs. Now if this is not collision resistant, what happens? It happens that h is x is equal to hs x dash, right? Now this can occur in two scenarios. Case 1 can be that these two are same. Okay, this will imply that h of x is equal to h of x dash, so that these inner inputs are same, so applying h of s on that will give you the output same. So this is case 1, which of course implies that h is not collision resistant, which is contradiction, not CR. And case 2 is the inside functions are different, so it maps to some y and this maps to some y dash. H of hs of x is y and hs of x dash is y dash. But then also, because the final output is same, that will imply that you will find such y and y dash for some x and x dash such that collision occurs in terms of function h. So this will also imply that h is not CR. So in both the cases, h hat being not collision resistant implies h being not collision resistant. So by contradiction we say that h dash is collision resistant. So that's it for today. Thank you.
Ma'am, I had
Yes.
two questions. Yeah. So one, my doubt is that when we say the word block cipher, so does that word block cipher means different meaning? For like in the book it is written that it's written somewhere block cipher is mentioned as pseudo-random permutation and somewhere it's written along with the modes of operation.
Okay, so I think I somewhere in last week or last week I was mentioning this also. So yes, block cipher can be used as pseudo-random permutation, and block cipher as in the cipher text, the encryption algorithm, in that way also in some context it can be used. And in some cases, like you saw that today in this Davis-Mayer construction for constructing fixed length compression function, collision resistant compression function, there also in ideal cipher model we assume the block cipher to be a PRP and we handle the construction then onwards. So it depends on the context.
So basically, should we understand block cipher as something that takes input in one particular block as a fixed length, maybe the padding
Yes,
or the bumper.
yes,
That so wherever that applies, so that becomes block cipher.
right. It of course it has to satisfy the property of cipher, so it has to have the cipher text, like it takes plain text as the input and outputs the ciphertext, and there is some key involved. With that you
And
can say this is a block cipher, and you can use that complete block as a pseudorandom function or pseudorandom permutation depending on whether it is invertible or not in presence of the
so
key.
when we say we are taking message as an input, so if we consider that block cipher as a pseudo random permutation, so then that it's not a message, then it's a seed value, is it like that?
Sorry, come again.
When we say that a block cipher can be taken as or is a pseudo random permutation,
Hmm.
then the input is not message, right? In that case, the input is a seed value
Seed
because we are
comes
not.
in the context of PRG, pseudorandom generator, but yes, you as already mentioned that all these primitives are can be built from one another given a PRP construction. So let's say you are using this block cipher as PRP. Now from this PRP you can generate PRG, then you can convert the role of seed and the input vice versa depending on, like in the GGM construction also, that where you use PRG to build a PRF, then the PRF key actually, or in other words the seed of the PRG becomes actually the key of the PRF, right?
Ma'am, in this case, basically I'm still getting confused because when we say it's a pseudo random permutation, it means it's a fixed length preserving scheme.
Mm-hmm.
So length preserving scheme is whatever is the input length will remain intact. The only thing is that the bits they get mixed. So
It is a
so
length
then
preserving pseudorandom function. So whatever is the property of pseudorandom function, that still needs to be held, and apart from that the restriction is that your output bit length is same as input bit length.
input different, right? So then the input, that what I'm question is the input that goes in the PRP.
Hmm.
What is that? It's not message, right? Because we are supposed to be checking. It's not message. That is what your question is.
See, the usually from the terminology point of view, message is used in place of plain text for an encryption scheme. So message is something generally used in case of encryption scheme, because given a message you want to encrypt it and generate ciphertext. And for PRF PRG, in this for PRF or PRP, you usually call it as input, but like these are just terminology. At the end of the day you have some function for which you have defined key space, you have defined input space or message space, whatever you say, and you have some output space defined. So
Okay.
usually for function like PRF pseudorandom function, for function you say it is input output pair, for encryption function you say it is plaintext ciphertext pair or message ciphertext pair, just varies.
Yeah. Okay, ma'am. So basically, pseudo. Okay. So maybe I'm getting confused with pseudo random generator and pseudo random computation. Pseudo random generator, as you rightly said, we need a seed value.
Pseudorandom
And yes,
generator needs a seed value which is secret. Yes.
and seed and a key also, right?
Pseudorandom generator does not have any key. It just has seeds which is secret, but pseudorandom permutation or pseudorandom function, there comes the concept of key which is secret.
Key and the input value.
Input you can query with, and the key is secret, but the function takes both key and input to evaluate the output.
And one more question I had in case of this SPN, this substitution computation network.
Achha,
So
I'm
we
just
have.
sorry to interrupt little bit, like maybe we can continue in the next session. Actually I have something to somewhere to go right now, so it's already 8. I'm very sorry to interrupt, but we can continue the next week with the conversations. Okay.
Okay.
Okay. Thank you very much.